So I'd now like to introduce Zhenan Bao, who's a professor of chemical engineering and material science at Stanford. Zhenan received her PhD in chemistry in 1995 from the University of Chicago and joined Bell Labs Lucent Technologies and worked there for 9 years before she joined the faculty at Stanford in 2004. She's known for her work throughout her career in organic field effect transistors, but most recently she's been doing very exciting work that she's going to tell us about in flexible conductors that, among other things, are leading to polymers that seem to have a sense of touch that can be used. She, too, has been widely recognized and decorated. Unfortunately, because of her 9-year industrial stint, she wasn't eligible for the Teacher Scholar Award, but she's been elected to the National Academy of Engineering and has received many other important recognitions of her work. So we're looking forward to hearing from you.
We start by saying that it's a pleasure for me to be here, even though, as Matt mentioned, I wasn't eligible for the Teacher Scholar Award. I was fortunate to have mentored two Dreyfus environmental chemistry postdoc fellows. One went on to Purdue, started his own academic career, and another one, Ji-Hye Park, is on the job market this year, so watch out for her. And in my work, we have been mainly kind of looking at chemistry from the point of view of how to design new materials, how to utilize chemistry to come up with concepts that can allow us to control the property of materials. It was nice to see the history of the Dreyfus Foundation and how the Dreyfus started from the materials aspect. So in here, I like to tell you about our journey towards now trying to develop future electronics where these electronics take the shape and the form factor like skin. So this is a piece of semiconducting material that we're making in my group. So as Matt mentioned, I spent a number of years in Bell Laboratories. There, my work was mainly focusing on understanding how do we design organic materials so that they can have electronic property that hopefully when they can catch up with those of inorganic electronic materials. So by the time when I left Bell Labs, we were already at a stage that we were able to make displays bendable and foldable, like this first flexible electronic paper. And also you heard from the first talk that with synthetic chemistry, essentially one can make any molecule they want. But what I was fascinated about was how can we just simply by moving one bond in a molecule or adding one atom in a molecule and to be able to completely change the property of these molecules, which is the design concept of these materials. But then at that point, we can already see that industry, even though flexible electronics wasn't yet commercialized at the time when I left Bell Labs, but we could already see that this is something that's going to happen in the future. So when I started my work in Stanford, I wanted to look for something that's further away, something that can allow us to really be able to use chemistry to develop new concepts. In the coincidence, I met a colleague from mechanical engineering. His name is Mark Kokowski. His group was making robotic cockroach. And these cockroach, you can see they have hooks on the hands of the cockroach that allows them to climb up the wall very fast. And I was very impressed when I saw this video. So I asked Mark, well, this is really cool. What are problems that you still need to address for these kinds of robot? Can flexible electronics be applied here? So he told me that, well, these cockroaches, they can climb up to the top of the wall, but then there's nothing to grab on, and they fall off from the wall. So he said, if you can make some sensors that can be put onto their hands, then they will have the sensory feedback, and potentially then they will be much smarter. And also there's this giant field I wasn't really familiar with at the time. That's the robotics field and the prosthesis. And people really need sensors to provide sensory feedback. So that's when we started thinking about, well, can we really do something with flexible polymer electronics and then make a difference in this area? So we started by looking into existing technologies and found actually none of them would meet the requirement. So we came up with a very simple solution. Here we take a rubber that we make them into pyramid shape because we found if we use a thin film of rubber, they will have a lot of hysteresis when we have pressure applied or force applied and remove the force. There's a significant delay due to the viscoelastic behavior of rubber. So we designed this shape, and then this allows the signal to return back to its original shape very quickly, because the pyramid tip being very small make it easily deformed. And these kinds of sensors can be made readily with simple imprinting methods. And because of the shape we use, it allows the sensors not only remove the hysteresis effect, but also at the same time being very sensitive. So sensitive so that it can detect the landing of a butterfly, as shown here. So with this kind of sensor, then we start exploring what are the possible applications with them. For example, this is placing the very thin and sensitive sensor onto the artery to detect the details of pulse wave. And from this nice shape of the pulse wave, one is able to get the blood pressure information. So this became a basis of a spin-off company that's venture funded in Silicon Valley. Right now we're developing non-invasive blood pressure monitoring wearables that can be used for infants as well as for adults. And more recently, we are finally able, after more than 10 years of the discussion with Mark, now we finally were able to start putting these kinds of sensors onto robot hand to be able to handle delicate objects. So once we started this initial work on trying to mimic the sense of touch from human skin, then we start kind of step back and think about, well, the human skin actually the function of the human skin is more than just simply sense touch, but rather the skin is able to sense touch, sense external stimuli, but also be able to convert this information into electrical signal that can be used to communicate with our brain. So essentially, there are sensing elements, but also signal processing elements that converts the analog signal, which is the absolute value or the amplitude of pressure, into electrical pulses, basically frequency signal that our brain can understand. And moreover, the electrical signal needs to be able to interface with our nerve system for our brain to understand. So all of these components are actually important components for our wearable electronic system. So essentially, skin is a wearable electronic system that if we can learn all of these different aspects from skin and be able to apply that to our future electronics, then this may potentially allow us to do very different things from what we can do currently. So this, after realizing this becomes the overarching goal of the research in the group to basically try to learn all of these aspects from skin and be able to develop the materials that will go into this. And of course, we're not the only group who is fascinated by skin. There are other research groups that are also trying to build artificial skin using very sophisticated transistor arrays and sensors. So here, these transistor arrays are very important because it allows us to know which pixel actually is sensing a certain target to allow us to reconstruct an image from the sensing. And that's also how our display is made. We have all these transistor arrays behind the liquid crystal to tell which pixel in the liquid crystal is being switched on and off so that we can see the moving image. But here, the problem is that if we use this same idea as how we build the displays to apply to a large sensing array, our hand alone has millions of sensors on our hand in the skin. And in that case, it will require huge amount of computing power to be able to process all the signal that comes to the microprocessor. So but the way our human process the signal is actually taking digital information, so basically electrical pulses. And these electrical pulses allows them to be combined in Synaptic Junction and have a pre-signal processing to take place to reduce the power consumption. And furthermore, the electrical pulses can transmit over very long distance without losing the information. Because if you have a simple amplitude of signal to transmit over long distance, it's very easy to, due to the loss of through these wires to lose the information. But digital signal, you can just count the number of pulses and be able to get the information. So it turns out the way our skin processes the information is through various kinds of mechanoreceptors. The way we are able to tell pressure, a large pressure versus low pressure, is by firing through these mechanoreceptors at a different frequency. So the larger the force we experience, the higher the frequency our mechanoreceptor will fire. So that's how we are able to tell a different pressure. So our goal becomes to first be able to mimic this kind of way of signal processing in our flexible electronics. And then we can use this as our basic platform to develop new materials and develop further increase the complexity. So here we designed an approach where we can use the pressure sensor to control the oscillation frequency of a small circuit, which consists of 6 transistors, and all of which can be made of flexible electronics. And then with this, we're able to show that the force sensing range and the frequency of output from these artificial mechanoreceptors can basically mimic those of the biological ones. And to further show that such a signal can be used to communicate with our brain, we collaborated with a colleague in bioengineering, Karl Desroff, who is the pioneer in optogenetics. then using genetically modified mouse whose brain region, in selective brain region, becomes sensitive to light stimulation, we can connect our artificial mechanoreceptor, which when we increase the pressure, then the frequency of output will increase. And then this is used to stimulate the brain of the mouse. And then we measure in the location of the stimulation the firing of the neurons in those regions. And these neurons are firing, we observe they fire at a similar frequency as those of the stimulation frequency. That indicates that the brain is indeed responding to the stimulation that we're using. So this is a relatively simple demonstration, but it shows that it's now possible to design an artificial device and use this to mimic all the functions that our human skin has, but only in one simple element. And then to take these mechanoreceptors, as I mentioned, the way our skin process signal at low power is that many of these sensors will all send their signal to synaptic junction. And there is a pre-signal processing at the synaptic junction to allow learning of the information. And then this information will further come together to the nerve fiber, and then nerve fiber will come together to nerve bundle, and eventually the signal is transmitted to our brain. So to take the next step, then is to have these sensors, so multiple sensors that we have shown earlier, and then coupled with ring oscillators. So this is several of these mechanoreceptors now coming together to a artificial synaptic junction. Then by making this type of structure, now we are able to take a step further to learn from the skin to build this system a little bit further. So we hope that with this, then we can now start to have even more complex structures and combine with machine learning to be able to truly make a artificial skin that mimics the way our skin functions and the processing signal. So now we have a basic kind of device platform to learn from skin. But then the other question we ask is, what else can we learn from skin? Skin is actually a fantastic material. It not only is able to sense information, process information, but also at the same time, skin is not only flexible, but also stretchable, biodegradable, and self-healable. And all of these properties are properties that our current electronics do not yet have. But if we're able to incorporate these properties into our future electronics, this may open up new possibilities. So now we have one single artificial mechanoreceptor. So our thinking is if we can develop new form of electronic materials that have the skin-like property, then we can start thinking about incorporating them into this general artificial skin platform and make them more complex, make them more skin-like over time, and see what they can do. One thing we think that we may be able to change is to change the future of electronics. Our current electronics are mostly based on silicon integrated circuits. And, based on silicon integrated circuits, they are rigid and brittle, but if we can use But if we can use this new generation of electronic materials, maybe we can make our electronics wearable. We can make them foldable and also be able to tolerate the strain that's needed to accommodate movement of human body, to accommodate the strain exerted when we bend the display into a very small radius. And if we want to put electronics inside the body onto the beating heart or onto our brain to map electrical signal, we also need to accommodate the movement as the heart beat, and also as we breathe, the brain will expand and contract by as much as 10%. So all of these new applications will require new materials, not only excellent electronic materials, but also at the same time electronic materials with new properties. So the key fundamental question becomes, how do we design skin-like electronic materials? And the most important constraints we face is that how do we design these materials without compromising the electronic properties in these materials, which is we want to add new functionality, but at the same time, these materials still need to be the best electronic materials possible. So we got interested in a type of chemistry that's related to dynamic chemistry. So here, most of the polymer network that we're working with, basically, in order to make them stretchable, we needed to have these junctions that can link the flexible polymers together so that when the strain is released, the polymer will be able to return to its original shape. And traditional rubber is typically cross-linked together with covalent bonds. But when these bonds break under high strain, they can no longer recover. There's a new generation of materials where these junctions that's connecting the polymer network is made of dynamic bonds. Basically, these are bonds that can have lower bond energy, and they're readily broken. But at room temperature, they can still recover and reform its original bond and allow the material to recover its original mechanical property. But the breakage of these bonds allows energy dissipation so that these material can tolerate high strain and also have a very large fracture energy. So this is the type of chemistry has mainly be related to these supramolecular chemistry and some reversible chemical bonds, and some of the examples are shown here. And these chemistry has been applied to make self-healing materials in recent years. So in our case, we want to see how we can utilize this kind of chemistry to utilize them in designing electronic materials with the properties that we need and be able to realize electronics that we need to build with a skin-like property. So the first generation of such material that we work with is this polymer network that's cross-linked together with these urea-based hydrogen bonding. The urea groups allows the breakage of these network when the material is under strain. And this material can self-heal when there's a scratch being induced. And because of the dynamic nature of this polymer network, the polymer can diffuse across these cracked region, and the chemical bonds can be reformed. And to make an electronic skin, then we incorporated nanostructured conductive particles to allow the material to be able to not only self-heal, but also be able to sense pressure, sense strain. That's why we call it the first self-healable electronic skin. But one issue with this material is that even though it self-heals, but it's highly viscoelastic, it's very able to tolerate extremely high strain, but it takes a while for the polymer to return to its original shape quickly. So in another word, we need a material that's also highly elastic. So our second generation material, we used the understanding of trying to balance the amount of covalent bonds versus the amount of dynamic bonds in the material to introduce macro cross-linkers without compromising the having a lot of hydrogen bonding. This allows us to make this now elastic material that can heal very quickly, within a minute. Most of the chemical bonds at the interface has already been recovered. But you can see just now that if there's a defect in this material, along the defective sites, that's where the crack can propagate and the material can still fail. So that led to us to think about additional molecular design that can solve this problem. So this is a recent generation of material where we, instead of a covalent bond combined with the dynamic bonds, we use two types of dynamic bonds, one being a very strong quadruple hydrogen bonding site, and one being a weaker hydrogen bonding site due to the steric hindrance introduced into these moieties. So the dynamic bonds still allows energy dissipation when the material is under strain, but with these very strong hydrogen bonding, if there's a defect in the material, these strong bonds will block the crack propagation through this material, and potentially our hypothesis is that this design can potentially allow the material to have a much higher fracture energy. So indeed, using this design, you can see we introduce a defect intentionally, but this material can still tolerate extremely high strain and being stretched to more than 12 times its original shape without forming any cracks. And it turned out this type of design actually can give us self-healing materials that are both stretchable and self-healable with the highest fracture energy that's realized for any self-healing elastic material. So combining this knowledge of designing stretchable and self-healing material and our previous knowledge in designing electrical dielectric materials for thin film transistors, then we can design a dielectric material that have the skin-like property, but at the same time be able to allow us to construct these transistors that's compatible with the best semiconducting material that's out there, and to be able to give us performance similar as if we use silicon dioxide, which is the best inorganic dielectric material that's known, and be able to give us electrical characteristic that we would expect for these semiconducting materials. And then taking from, for thin film transistor construction, we also need semiconducting material using similar molecular design concept of introducing these hydrogen bonding dynamic chemistry into the semiconducting material. Then we were able to turn the normally brittle polymer semiconductors now also into stretchable polymer semiconductor. So over the past number of years, with the understanding of designing these materials, now we have a collection of electronic material ranging from conductors to semiconductors, which are stretchable, self-healable, or biodegradable, that all have these new added skin-like property, but at the same time without compromising enhancing their electronic property. So now we are at a stage where we have a number of materials, so we can start to think about how we incorporate them into actual electronic devices. So that took us another few years to develop, basically taking these materials, and again, a lot of chemistry goes into that to come up with photo patterning methods so that we can pattern each individual layers of these skin-like electronic material into actual device structure so that we can make not only just one device, but hundreds of them and thousands of them so that we can see what we can do with these materials. So currently, our electronic circuit looks like this. They can be fabricated onto stretchable platform, and we monitor the current output from one of these devices, showing unchanged current output, even when the device is under extreme mechanical strain, and still be able to have the same amount of current output. And with these fabrication and the materials, now we can start building some simple elements that are important to build our future electronics. So for example, this is the active matrix array with 10 by 10 transistors that can allow us to map the shape of a small object using this active matrix array. These are basic circuit building blocks that are needed to make any logic circuits and analog circuits. So here, the circuit can function not only at 0% strain, but also 100% strain. One of these circuits, we want to show the functions of this circuit. So this is a circuit with 4 transistors and has the ability to amplify signal. So here, our sensor sends the pulse wave, but the signal-to-noise ratio is very low. But if we put this little circuit right next to the sensor, then it amplifies the signal by 10 times. And now our best circuit can amplify the signal by 100 times. So it can significantly improve the signal-to-noise level. So basically performing the signal processing at the front end where the sensor is. So basically, the wearable electronic system will all have sensing elements, data conditioning elements, basically the amplification and also digitization of the signal. And finally, the signal will go to the microprocessor to get processed. So we envision the skin-like materials, the skin-like electronics will mostly play important role in these sensing element and the data conditioning element to allow us to really make distributed sensors over very large area. And over time, our vision is that currently, we all carry a smartphone, which allows us to gather information and communicate through the internet. But over time, we envision that our smartphone is going to dissolve into the clothes we wear and the electronics that are mounted on the surface of our body and implanted inside our body. And this may become a way for us to communicate and connect with our external world. And this is, of course, something that cannot be realized with one single research group. So 2 years ago in Stanford, I started a Stanford Wearable Electronics initiative. The goal is to gather people from different disciplines to work together towards this common goal, towards being able to really be able to realize skin-inspired electronics in different applications. And here, towards that goal, we started collaboration with people in the medical school in looking at, for example, wireless implantable sensors, starting from our very early pressure sensors and now implanting them inside the brain to measure brain pressure and implanted into the hand to monitor the repair of tendon. This is another implanted device wrapping the sensor, wireless sensor, around the artery that is used to monitor whether there's a cloggage inside the artery. And finally, in terms of a biointerface, we start to take the first steps to making these electronics to be able to stimulate the nerve, to measure electrical current on the beating heart, and now also implanting these skin-like sensors that both stimulate the nerve as well as sensing chemical signal from the brain. So to summarize, here, we started by asking a very simple question of trying to learn how our skin senses, which took us into a journey of trying to use that to think about how we design future electronic materials and use chemistry to enable us to develop a new generation of electronics. And now we are at a stage where we have a number of materials that can allow us to start to explore new possibilities with this direction. But at the same time, there are a lot to be understood in terms of the fundamental science. And furthermore, how do we really use the power of chemistry to be able to engineer materials from molecular level to achieve the properties that we want them to have. Finally, of course, I'd like to thank the funding agencies, many collaborators, and the students. They are so creative and always so enthusiastic and hardworking. They are really the people to make this work possible. And again, it's my pleasure to be speaking here. Be happy to answer any questions you have. Thank you.
So can you tell us about the domain size? They can have some spatial resolution for pressure sensing. How about the temperature sensing, the status of that?
Yeah, so for the pressure sensing, you're probably referring to the pixel size that can be achieved. So in our case, the smallest pixel we have made is a few hundred micron. And going down to tens of micron is relatively straightforward. And it turns out in our hand, actually the highest resolution needed for sense object is only in the order of tens of micron. And in most cases, these sensors are even millimeters apart. For temperature sensing, there are strategies actually quite a number of strategies to realize temperature sensing. I did not talk about here. There are resistive-based temperature sensing, and there are also little circuits that we develop that can sense temperature, but without being disturbed by the strain that's being applied.
I guess I had a fairly basic question about the self-healing aspect of it. So if you take something that's stretchable, styrene, butadiene, rubber, or something like that, why can't I take two pieces of that, put it together, and have the crystalline, non-crystalline units all get back to where they were? But in these materials, you do. So what's different about the way that these are elastomers?
Yeah, so for the thermoplastic, such as the SEBS you mentioned, if you heat it, then the molecules at the interface can, through van der Waals interaction, to basically re-adhere with each other, for the two pieces to re-adhere with each other. So that mechanism would be based on intermolecular mixing. You can also call it self-healing, because many people have, different people have different definition for self-healing. But in that case, it does require some level of heating to allow this intermolecular mixing. And in the material that we work with, it relies both on the molecular movement to allow the reactive group to find each other, but as well as the chemical bonding. So potentially it can allow the bonding to be stronger at the interface. But you're
So I guess, is it inherently different then? So if you were to cut one of your materials and keep it at minus 100 degrees, would it would it be that you wouldn't call it self-healing, except that it works at room temperature instead of
so if the material has a very, very low glass transition temperature, then it's possible to reconnect or heal at low temperature, sub-room temperature.
Sorry.
So first of all, congratulations. That was an extremely interesting mix of science and engineering. My question is, does it play into the issue of reconnecting neural networks? In other words, paralysis caused by severance of neural networks. Does this hold possibilities for that?
Mm-hmm. Yes, this is something we are looking into. To reconnect a neural network, there is the brute force method of sticking electrodes into the brain and then try to do electrical stimulation. But there's also other possibilities. One possibility we're looking at, which I didn't talk about here, is to genetically direct where the conducting elements can actually grow inside the brain. So then if we're able to do that, then we can actually reconnect regions of the brains that may become disconnected or alter the way the different regions of brain can communicate with each other.
So I had a question about the memory of the material. So you stretch it sufficiently. How do all the right pieces come back into the right place? You'd mentioned sort of the strong and the weak H bonds, but is that enough? Can you pattern into that something specific so that everything ends up back in the right place? Or do you end up losing some information eventually? Like if you stretched a protein and expected it to refold, at some point, it's not going to find the right partners again.
Yeah, so the driving force for the molecule to return to its original shape, basically it's entropy driven. So when you strain it, the coil structure becomes basically aligned, and but then when you release the strain, it wants to go back to the coiled, more disordered state.
But why? But what would drive it to go to the same coil?
Right, exactly.
Yeah.
So that's why the nodes are important. That's why we need those nodes to basically drag them back to the original location. And then, of course, if we have only weak dynamic bonds, then it cannot go completely back because those bonds are too weak. So that's why we need to have also strong bonding and some weaker bonding in this molecular design.
And you find that sufficient for the memory of the material?
That's right.
That's very cool.
Within certain amount of strain. Of course, if you apply super high strain, and then this would not be applicable anymore. So within 100% strain, then the strong dynamic bond is sufficient to allow the material to go back.
That's amazing. Thank you.
I loved your. I loved your talk. I wondered about the idea possibly of using registry points. If you thought about that, so that you could, this is following up on your question, that there'd be a place that much more strongly wants to bind, and that would help make everything go into registry.
Yeah, that's an interesting idea, especially I think when a material is on a certain substrate, then one can think about playing with the chemistry on substrate and this registry idea. Yeah, that's a very interesting idea.
Thank you very much.
Thank you.